soaking the chip in a strong paint solvent known as methyl ethyl ketone, MEK, did not dissolve the chip. Ha, no zinc, and now this. It's not looking like paint, folks. And that's why I soaked the chip initially several finally in the methyl ethyl ketone was to see if they would dissolve. And then I soaked paint samples as well, and they did show dissolution, dissolving, and very much limpness in these paint samples in the MEK. Well, that's what it's for. It's a paint solvent. Whereas this material, and here's photos after the soaking, it's very interesting. The red surface swelled, and you can see now porosity. And if you look closely, you'll see a red region, which is rich in iron oxide and silicon oxide. Then you see some other regions which are more silvery colored. What we found is that this, and the carbon is swept out too. Well, let me show you the data, because I've been trying to explain it with my hands. I like data. So this is post-MEK soaking, 55 hours with some agitation. We see regions of separation. The silicon has been separated from the aluminum. Where tiny aluminum peak, huge silicon and oxygen peaks. Silicon oxide. And here you see aluminum, again, in a different region we found with a small oxygen peak. Here there's enough oxygen to oxidize the silicon. Here there is not enough oxygen to oxidize all of the aluminum. When you have small particles of aluminum in the air, you typically get a surface coating very quickly, actually, of aluminum oxide, which protects the inside aluminum from getting oxidized. Passivation, I believe is the term. And Jeff Farrer is an expert working with these machines now for years. Verified there's too much aluminum for it all to be oxidized here. On the other hand, the iron, which is enriched in another region, shows a very large oxygen peak, and there was plenty of oxygen to oxidize all of the iron. See, so again, thermite, well, just remember that aluminum, at least some elemental aluminum, probably quite a lot. It's a little hard to quantify with this method. Jeff is working on the TEM to pin that down for you. But elemental aluminum, very strongly evidenced here. Iron oxide, again, very strongly evidenced. Those are the components of thermite. Coming up, let me do that and we'll come back here. Thermite, you mix aluminum powder and iron oxide powders. The finer the powder, the faster it burns. Okay? And anyway, you mix those together and you heat it up enough. That's another factor. The finer the powder, the lower temperature is required to get it to ignite. The result of this chemical reaction is that the oxygen transfers over to the aluminum. We say the iron oxide is reduced, the aluminum is oxidized to form aluminum oxide, which is the white plume you see here drifting away, and molten iron, the yellow, white hot molten iron that you see. In other words, there's a great deal of energy released in this reaction. Temperatures upwards of 3,000 centigrade. These sparks that you see coming off molten iron, you see, if I spray water in the air, it forms what?
Droplets.
Droplets, good. They're more or less spherical, and that's because surface tension pulls the liquid into a sphere. It does the same thing with iron. If you, as you see here, eject molten iron into the air, it will form globules and droplets. Small ones will form pretty good, decent spheres. And then that's how you get spheres. So if you see a spherical iron in the dust after it's cooled, you say, well, this has got to be molten at one time. I mean, nobody's in there carving out little spheres, right? It's just forms by nature. And this is how you can do it with the thermitic reaction. And let's go back. We go to still higher magnification. Jeff did this for the first time. 50,000 power here using a scanning electron microscope. And what we find, I'll have to show you this a little later. It's in our paper too. Look, computer scientists, you say, I want to see the hard data and detailed explanation. Please read the paper. Obviously, I can't cover all of that, or I can read the paper to you, but it's 25 pages long. And some of you might get bored if I did that, so I won't. But these grains that you see here, these faceted grains, the brighter grains, are iron oxide, rich in iron oxide. And the plates that you see here, which are about 40 nanometers thick, are rich in aluminum. And there's silicon and oxygen as well. It's a very interesting structure. And then you see this carbon-rich stuff, this matrix surrounding it, and that's what's eaten out by the MEK clearly, as you then separate aluminum from silicon and iron oxide from the other materials. It's really, and the carbon comes out and is depleted after the soak in MEK. Very interesting. Oh, I'm glad we did that MEK soak. And the reason was because we wanted to see if the stuff would dissolve. It didn't, but it separated out. We got a bonus. It's, I guess, serendipity. The grains here, the iron oxide grains, are about 100 nanometers across. And again, Jeff is using TEM to refine this to determine what oxide. We're not real sure which of the iron oxides. It looks like Fe2O3, but we'd like to pin that down. It turns out it's not real important for our argument here, which is that there is iron oxide. And then the thermite reaction can proceed with aluminum. Okay, I've already gone through this. Oh, plus the organic. This is high carbon material out here. It's not random building stuff mixed together. Because of the uniformity, for example, of the particles, the grains that have the iron oxide, and of course the uniformity of these plates, which we see in other images as well, containing the aluminum. There's the reaction. Now here's something I'd like you to understand. Thermite, which is ordinary, conventional thermite, is, and you can buy it on eBay. Not necessarily recommending that you do, but you can. It's not a secret. I'm not telling the terrorists, that's what this guy Martin, by the way, said. You can't talk about thermite. He threatened me with legal action if I talk about thermite, and sent that to the BYU administrators. And I said, look, Martin, get serious. You can buy this stuff on eBay. I'm not revealing state secrets here. Now, nanothermite, you cannot buy on eBay, mind you. But it's also published, so it's not a state secret. But anyway, the ultrafine form, which is when you get down to about 100 nanometers for at least one of the components, iron oxide or aluminum, then that's called nanothermite, also called super thermite. And here you have a picture. This is from the Livermore National Lab, not too far from here. And this is an image, again, taken with an electron microscope. They've made the iron oxide green and the aluminum red. You see, they're not, the mixing is quite good here. It's called, preparing this for action. And when you heat it up, they actually show a photo of super thermite exploding. So this is ultra fine grains, right? Tiny, tiny. And that is explosive. You can actually tailor it, but I should say it can be explosive if you want me to be. It can be fast explosive, slow explosive, and so on. But wait, we still got carbon and silicon. Where are those coming from? See, here they've just got these two components. Well, we'll find out. I guess you'll have to wait just a minute because I want to show you something first. We took one of these red chips, we took several actually and did this, 4 of them. Actually, presented data in the paper.